All right, so let's continue. Causes of concurrency. In user space, the need for synchronization stems from the fact that programs are scheduled preemptively at the will of the scheduler. That's an important fact. So, why do we need synchronization? The fact that we have lots of programs running at the same time, even though it may not seem like it, because we have this fact that, okay, well, each program is in some sort of queue, right? Each task, T1, T2, T3, and so on. And each one gets like some sort of fair share of CPU as time goes on. But keep in mind that that's only CPU one, right? Now we're in a really weird world where we have more CPUs now. So they also have tasks too running at the same time. So this is true concurrency at this point, right? In the world where we were thinking about only one single thread, one single core, it made sense to think about processes running one at a time, but just switching really, really fast through context switches. And essentially, it's just looking like everything's running at once. But now that we're bringing in like two CPUs, two threads, or even more CPUs, you do have tasks that actually run concurrently at this point. So at some point, these two tasks, right, they're going to end up needing to share the same piece of data. Okay? So it's all fair. It's not, even though they're restricted in terms of their own virtual address spaces, there's always concepts of like shared memory, for example, because these are just tasks. There's no like notion of like, anyway, I don't want to get too far into that, but yeah, they do end up sharing some data because these could be two different threads, not exactly processes. Let's think of it that way. Okay, I think it's easier to have that mental model. So because a process can be preempted at any time and another process can be scheduled onto the processor, a process can be involuntarily preempted in the middle of accessing critical region. So remember, a process has a task or a process has a lock as is in the room. Okay, it's in the room, so that room is a critical region. It has a lock. No one else can come in. Okay, so now if I am preempted, I'm in the room, I can't execute anymore, a new process comes in. If the newly scheduled process comes in as in like wanting to jiggle the door, if the newly scheduled process then enters the same critical region, say if two processes manipulate the same shared memory or write to the same file descriptor, a race can occur. So what it's saying is that if I allow someone else in, if I didn't have that door locked, someone comes in, then while I am away or sleeping, something like that, because I'm preempted, they could be like messing around with things and messing up the way I wanted the room arranged for my work to get done. So that's what we call that race condition, where someone starts fiddling with something that I didn't want and I didn't expect that to happen. So the same problem can occur with multiple single-threaded processes sharing files. So this also applies to files, not just memory and data, okay, or within a single program with signals, because signals can occur asynchronously. This type of concurrency in which two things do not actually happen at the same time, but interleave with each other such that they might as well, is called pseudo-concurrency. So remember we were working with these examples here. So some of these examples will always show like thread 1, thread 2 trying to execute things at exactly the same time. But you can have situations where they are at some points executing, I'm not going to even find it, but at some points they're executing at the same time and conflicting, and at various points one goes to sleep and then is at a different place than the other. But the fact is that they're both in the critical region. If they both touch the critical region at any point in time, that's basically concurrency. And that's the reason why they're saying that's called pseudo-concurrency. In my mind, it's just concurrency. Concurrency is still concurrency. You run the risk of race conditions and bad things happening. So It's like telling your mom that you didn't have any candy at all, but you licked the candy. You licked the candy, therefore you did have candy. I don't care what it is. If you have kids, you would know. I don't care what it is. If you licked the candy, you ate the candy. So, if you have a symmetrical multiprocessing machine, two processes can actually be executed in a critical region at the exact same time. That is called true concurrency. Although the causes and semantics of true versus pseudo, okay, concurrency are different, they both result in the same race conditions and require the same sort of protection. Exactly, right? So if you're in the critical region, at any point in time where someone else is in the critical region, then you're going to cause a race condition regardless, or potentially. So the kernel has similar causes of concurrency. So this is what could happen. All right, so interrupts. An interrupt can occur asynchronously at almost any time, interrupting the currently executing code. So how should I put this? So we know that when we have hardware, we have like 5 pieces of hardware, for example, and any one of them can trigger interrupts, okay, at any time when a task is running. So if a task is running and an interrupt occurs, the CPU and OS have to work to get that interrupt handled, okay? And because of that, that interrupt can fit around with things that, again, like the process that just got preempted probably might need. Not only that, you have other interrupts that are happening, and the CPU, other CPUs, right? Other CPUs are handling those interrupts. And maybe those 2 interrupts, those 3, those 4 interrupts all share some sort of data with each other. And that's where you also need to consider concurrency or handling it. You have soft IRQs and tasklets. So we know this one already, right? Like soft IRQs, we can execute multiple soft IRQs at the same time, or even like take one type of soft IRQ. There could be another soft IRQ of the same type executing at the same time too. And just to refresh everyone's memory, a soft IRQ is kind of like the bottom half handler of an interrupt, the long part of the interrupt where we have a lot of code to execute because we can't execute big things during the top half of the interrupt, which is a regular interrupt handler. Top half usually will set up the data, set up the state of the world for the bottom half to execute. That's where soft IRQs come in. Those are the handlers that will do all the bigger things after the top half. Or tasklet, which is you could think of that as like a lower priority soft IRQ. It is basically a type of soft IRQ, but just executed at a different place. And also the same task that the multiple tasklets can execute at the same time, but a tasklet of the same type cannot be executed at the same time. So, but that's still, the key word here is like at the same time. So you still are in a situation for thinking about concurrency, right? So at almost any time, interrupting the currently executing code. Kernel preemption. So because the kernel is preemptive, one task in the kernel can preempt another. So maybe multiple system calls. Sleeping and synchronization with user space. A task in the kernel can sleep and thus invoke the scheduler, resulting in the running of a new process. Okay, so just remember that in kernel space, we can create new tasks too to do things. And those tasks are able to sleep because of some blocking operation. Now, you're left in a situation where if that task ends up sleeping, and it was working on some shared data or data that could be accessed by other tasks in the kernel, then we're running into a case of concurrency. So if you think about it, concurrency exists even without this extra CPU. This task could have been running and accessing some shared data, goes asleep, and this task here could actually be accessing that same piece of data too. So you want to just make sure that, well, if this task is forced to go to sleep operating on shared data, we have to make sure that that shared data is locked so that when this task is now executing in the queue, If it tries to access that shared data, it won't be able to, thus going back to sleep. And then, yeah. So this is possible, right? Like, it's not just only having two CPUs at the same time executing tasks, but it could happen in this linear fashion too, because of that preemption, right? Like, task one executes a little bit, accessing shared data, then it gets preempted, so back into the ready queue. Now task two is in the running queue, and then it is now wanting to access that same data task one wanted. So what do we do there, right? So that's why we have locking, to prevent that shared data from being corrupted by some other thread. When I say corrupted, I don't mean like broken. I just mean like fiddled around with in a way that we don't want, or at least in a way that task one doesn't want. So symmetric multiprocessing. So again, like, this is the example that I introduced right here, where two CPUs, where you have two tasks, right? Two tasks from those CPUs are accessing shared data. So kernel developers need to understand and prepare for these causes of concurrency. It is a major bug if an interrupt occurs in the middle of code that is manipulating a resource and the interrupt handler can access the same resource. So it is a major bug if an interrupt occurs in the middle of code that is manipulating a resource, and then the interrupt handler can access that same resource, right? So user space code, any type of code, kernel task, whatever, is accessing some sort of resource, and then the interrupt comes in, and of course you have to handle it. You have to run some interrupt handler. It turns out that interrupt handler wants to also mess with that same resource. So you need to be prepared for this part, right? Similarly, if it is a bug if the kernel code is preemptive while it's accessing a shared resource. Likewise, it is a bug if code in the kernel sleeps while in the middle of a critical section. Finally, two processors should never simultaneously access the same piece of data. With a clear picture of what data needs protection, it is not hard to provide the locking to keep the system stable. So you can solve all this with proper locking, like knowing what to lock and when to unlock. It's not, well, the book is hinting that it's not that hard if you understand what your critical region is. And I think it's even easier if you know how to leverage your API. Me, I don't know. So that's practice. So we have to just work on a few situations where we have concurrency involved, and then just using the right APIs, locking, testing. I think we develop a sense. Rather, the hard part is identifying, right here. Rather, the hard part is identifying these conditions and realizing that to prevent concurrency, you need some form of protection. There we go. Okay? I'm not going to even repeat this because he is right here. Let us reiterate this point because it is important. Implementing the actual locking in your code to protect shared data is not difficult, especially when done early on during the design phase of development. So I'm a big fan of planning things out, as you can see, like where I kind of write out my plan in my videos before I even like implement the code. I'm a big fan of planning because you can at least knock out all the easy things to consider. So design phase of development is quite important because it allows you to clarify the problem and think about how to navigate in that spaghetti code base. No offense, Linux kernel. The tricky part is identifying the actual shared data and the corresponding critical sections. Okay, so that's again, the tricky part is identifying the actual shared data and the corresponding critical sections. This is why designing locking into your code from the get-go and not as an afterthought is of paramount importance. It can be difficult to go in ex post, meaning it's hard to like handle locking after you have done all your code, like written all your code, because then it becomes very confusing to identify the critical regions and retrofit locking into the existing code. Retrofitting is always hard, especially when things are written in a way that's kind of set in stone. It's really hard. The resulting code is often not pretty either. So now the takeaway from this is to always design proper locking into your code from the beginning. Code that is safe from concurrent access from an interrupt handler is said to be interrupt safe. Code that is safe from concurrency on symmetrical multiprocessing machines is SMP safe. code that is safe from concurrency with kernel preemption is preempt safe. The actual mechanisms used to provide synchronization and protection against race conditions in all these cases is covered in the next chapter. So we're just focused on conceptual things this chapter. So knowing what to protect. Identifying what data specifically needs protection is vital, because any data that can be accessed concurrently almost assuredly needs protection. It is often easier to identify what data does not need protection and work from there. So figure out what you don't need protection, and then just go from there. Yeah, there we go. Obviously, any data that is local to one particular thread of execution does not need protection, because only that thread can access the data. For example, local automatic variables and dynamically allocated data structures whose address is stored only on the stack do not need any sort of locking because they exist solely on the stack of the executing thread. Okay, what does that mean? Okay, so let's parse that again. Obviously, any data that is local to one particular thread of execution does not need protection. Okay, so whenever we create new threads, right? So let's say this is thread 1, thread 2, okay? We know that they access, or oops. Oh yeah, no, that's true. We know that they access the same like virtual address space for the heap, right? And then code, and then like globals, constants, whatever. Okay, but they do get their own like set of reg, I think, and stack, and then other things too. I'm not sure if files are shared or whatever, but that's not important for this. What I'm trying to say is that whenever you have multiple threads of the same process, for example, the stack here is knowing that they get their own stack is important, because why? Whenever you have a function, any variable you declare inside that function, okay, is actually in that stack, in their own separate stack. So that's why you don't really need to care. If you're manipulating something inside that function, that's its own stack in this case. But now when you actually do a malloc, right, on that piece here, then you're putting it into the heap. That's when you start to really care, because it could be shared. But if you're mallocing inside that function, you're not passing it around. If it's this malloc happens in here, then that's actually, you know, since this data here is different in a different stack, it's going to get a different memory address, if that makes sense. But if you malloc outside and you pass in the pointer here, there's a huge chance that they're actually shared in the heap. But if you malloc in here, they'll get a different pointer anyway. So anytime you see like data, or I don't want to be absolute, but if you see data that is declared and defined inside the function, keep in mind that it could be on the stack, right? And so if they're on a different part, if they're on different stacks, then it's something that you don't really have to consider concurrency with. But if you have something out here, then that becomes a different story. That's considered shared data at this point, because it's going to be in here. Okay? So only that thread can access the data, right? So only that thread, if we go back, the data is all in here if it's on the stack. For example, local automatic variables and dynamically allocated data structures whose address solely on the stack. So that's the important point, right? Local automatic variables, which is basically anything that is not malloced, right? Anything that's just like int x equals 5, right? That is the local automatic variable. And then the next part is and dynamically allocated data structures whose address is only stored on the stack. That's if, like, let's say you declare int y, right, pointer to an int, and then you do y equals malloc, whatever, inside that function. Well, that pointer only exists in the stack anyway, because you declared it inside the stack and inside the function, which means that it's inside its own stack. It means it gets its own stack. There we go. Okay. But you know what I mean. Like if it's inside that function, if you're creating something inside that function and that thread is assigned to that function, then it's fine. They do not need any sort of locking because they exist solely on the stack of the executing thread. Likewise, data that is accessed only by a specific task does not require locking because a process can execute only on one processor at a time. So what does need locking? Most global kernel data structures do. A good rule of thumb is that if another thread of execution can access the data needs some sort of locking. If anyone else can see it, lock it. Remember, lock data, don't lock code. Okay, lock variables, right? Don't lock execution of things. Like lock things that manipulate that data. So if you can access any variable outside a function, chances are you probably need to lock it. That's what this thing is trying to say. Okay? If you can't access any variables outside of the function because it's local to that function and your thread is running on that function, then it doesn't matter. So, okay. I hope that makes it clear. Config options, SMP versus UP. Okay, so SMP, symmetric multiprocessing versus UP. I don't know what that means. Let's figure it out right now. But you can configure the kernel to work in SMP mode or whatever UP mode this is. So because the Linux kernel is configurable at compile time, remember we can configure the kernel to compile various features through these feature flags. It makes sense that you can tailor the kernel. So that's the cool thing about Linux, specifically for a given machine. Most important, the config SMP configure options controls whether the kernel supports SMP. So if you have like 8 cores, 8 threads, whatever, physically, and you turn this option off, you don't support SMP. Many locking issues disappear on uniprocessor machines. Oh, uniprocessor. Okay. Okay. So we don't have to care as much, but there is some care still because of this preemption problem, right? Just don't forget, it's not that when we're in a uniprocessor machine that we don't care about concurrency at all. We do care about some. It's just that now the problem space has been reduced a lot in this case to this point where we only care about the preemptive concurrent problem. Consequently, when config SMP is unset, unnecessary code is not compiled into the kernel image. For example, such configuration enables uniprocessor machines to forego the overhead of spin locks. The same trick applies to config preempt, the configure option enabling kernel preemption. This was an excellent design decision. The kernel maintains one clean source base, and the various locking mechanisms are used as needed. Different combinations of config SMP and config preempt on different architectures compile varying locking support. In your code, provide appropriate protection for a most pessimistic case. Whoa. In your code, provide appropriate protection for the most pessimistic case. Oh, okay, so just always assume that's SMP. Okay, so SMP with kernel preemption in all the scenarios would be covered. So if you actually just assume SMP all the time, you will cover all your concurrent scenarios. Good to know. So whenever you write kernel code, you should ask yourself these questions. Is the data global? Can a thread of execution other than the current one access it? Meaning, is it shared? Okay. Is the data shared between process context and interrupt context? Meaning that is the data accessible in interrupt handlers and also your user space process? Is it shared between 2 different interrupt handlers? So 2 interrupts can also access that variable? If a process is preempted while accessing this data, can the newly scheduled process access that same data? So if thread 1 is accessing that data, can there be a case where if thread 1 is preempted, thread 2 comes in and tries to access that data? Is that possible? Can the current process sleep on anything? Okay, if it does, in what state does that leave any shared data? Okay, so is it possible that if a thread is accessing some shared variable data, whatever, is it possible that it might go to sleep at some point due to some sort of IO blocking or other resource that it needs to wait on, like a lock or whatever? Well, what happens to that shared data, right? What prevents the data from being freed out from under me? meaning that thread 2 can free that thing, and while thread 1 was needing it and happened to have gone to sleep, what happens if this function is called again on another processor? Okay, given the preceding points, how am I going to ensure that my code is safe from concurrency? So basically, if all of this applies, you need to care about concurrency. Yeah, if all of this applies, you need to care. So in short, nearly all global and shared data in the kernel requires some form of synchronization methods discussed in the next chapter. Okay, deadlocks. Okay, a deadlock is a condition involving one or more threads of execution and one or more resources, such that each thread waits for one of the resources. Okay, but all resources are already held. Okay, so a deadlock is basically when you have one or more threads, okay, that are interested in one or more resources, and each thread wants to wait for one of those resources to be available, but all the resources are not available. Okay, so that leaves that thread to be just waiting around, and other threads are also waiting around because those threads need something that thread already has, right? So remember, when you don't have a resource, what happens? You go to sleep. Okay? Now, if you're holding on to a resource that another thread needs, and you are also sleeping because you need a resource for another thread, well, that thread needs your resource, it goes to sleep. You wake up and you're like, oh crap, I don't have that resource yet because that thread still has it, it's going to sleep. And so it goes to sleep. Then this other thread wakes up and it's like, oh, what? I still don't have that resource because that thread has it and is sleeping, so I'm just going to sleep. So that's a deadlock. No progress is made, and basically nothing happens. You just lock up. So the threads all wait for each other, but they never make any progress towards releasing the resources they already hold. Therefore, none of the threads can continue, which results in a deadlock. A good analogy is a four-way traffic stop. If each car at the stop decides to wait for the other cars before going, no car will ever proceed, and we have a traffic deadlock. The simplest example of a deadlock is a self-deadlock. Oh my gosh, when you deadlock yourself? Okay, if a thread of execution attempts to acquire a lock it already holds, it has to wait for the lock to be released. But it will never release the lock because it is busy waiting for the lock, and the result is a deadlock. So if you try to acquire the lock 2 times, so acquire lock again, and then wait for the lock to be available. Okay, that's a pretty bad bug because this happens. This is real actually. This if you can think about like a recursion, where you call that function where you acquire the lock again, right? That happens. So some kernels prevent this type of deadlock by providing recursive locks. These are locks that a single thread of execution may acquire multiple times. Linux thankfully does not provide recursive locks. This is widely considered a good thing. Although recursive locks might alleviate the self-deadlock problem, they are very readily lead to sloppy locking semantics. So there are solutions for this, but Linux doesn't provide it because it leads to just hard to read code. Okay. So I'm starting to get this feeling that in order to work in the kernel, you have to like take a lot of care, because I think the philosophy here is simplicity trumps all. And if you just take care into what you're doing, you can write, you don't have to have so much helpers around to get things done, and I think code ends up being cleaner that way. Okay. Similarly, consider end threads and end locks. If each thread holds a lock that the other thread wants, all threads block while waiting for their respective locks to become available. The most common example is with 2 threads and 2 locks, which is often called a deadly embrace, or the ABBA deadlock. Wait. So when 2 threads, if each thread holds a lock that the other thread wants, and all threads block while waiting for their respective locks to become available, the most common examples with 2 threads and 2 locks, which is often called the deadly embrace. I like that, the deadly embrace. Okay, so basically what it's trying to say is that, okay, you have two threads here. Okay, so you acquire lock A, so just, any type of lock. Thread 2 is running 2 at the same time, it acquires lock B. And then thread 1 wants to also acquire lock B, because locks, you can acquire as many locks as you want to work with code, right? So it tries to acquire lock B, but then thread 2 also tries to acquire lock A. Well, lock B is already being held by thread 2. Lock A is already held by lock A is already being held by thread 1. So since lock B is being held by thread 2, thread 1 goes to sleep. Wait for lock B. Thread 2, when it wants to acquire lock A, well, thread 1 has it, so it has to wait for lock A, goes to sleep. So both are now sleeping. Okay? So each thread is waiting for the other, and neither thread will ever release its original lock. Why won't it ever release its original lock? Well, it's because of this. Like, you're trying to acquire two locks, and you can't seem to acquire the second lock. And, when you think about it, if you can't acquire the second lock, what's the only thing you can do here? You can just sleep. Okay? Well, the other guy or girl wants to get the other lock, but you have that lock, but you're sleeping. So it just goes, okay, I'm just gonna go sleep too. So anyway, prevention of deadlock scenarios is important. Although it is difficult to prove that code is free of deadlocks, you can write deadlock-free code. A few simple rules go a long way. So you can actually prevent this pretty reliably if you follow these set of guidances here. So basically, implement lock ordering. Nested locks must always be obtained in the same order. What this prevents the deadly embrace lock. Document the lock ordering so others will follow it. So what does that mean, right? So it means like this. So if you are wanting to acquire lock B, for example, if you want to acquire lock B and you're acquiring multiple locks, you must always acquire lock A first. So that means thread 2 is breaking the rules here. If thread 2 had acquired lock A first and not lock B because it wanted lock B, it would have gone to sleep, allowing thread 1 to acquire lock B, because thread 2 never got lock B because it has to get lock A before lock B. Now, thread 1 gets to do stuff now, and then releases lock B, releases lock A, and then thread 2 now can acquire lock A, acquire lock B, and make its own progress too. So always have that consistent ordering. Prevent starvation. Ask yourself, does this code always finish? If food does not occur, will the bar wait forever? So basically, if this code does not happen, will the thread end up waiting forever? Okay, so that's something you have to take care of. Do not double acquire the same lock. So don't say acquire lock A, try to acquire lock A. That's silly. And then design for simplicity. Complexity in your locking scheme invites deadlocks. So just try to keep it as simple as possible. I guess I'm going to just say it, use the dumbest thing possible. Do the dumbest thing possible. If you need to write all your code in one function with that critical region in there and the locking, just do it. It's less risk. The first point is most important and worth stressing. So the first point is the lock ordering part. If two or more locks are acquired at the same time, they must always be acquired in the same order. Let's assume you have a cat, dog, and fox locks that protect data structures of the same name. Now, assume you have a function that needs to work on all three of these data structures simultaneously, perhaps to copy data between them. Whatever the case, the data structures require locking to ensure safe access. If one function acquires the locks in the order cat, dog, and then fox, remember these are locks, okay? The cat lock, the dog lock, and the fox lock. Then every other function must obtain these locks, or a subset of them, okay? In the same order. So if I wanted to get fox, I need to get cat and dog first. Okay? If I want to get dog only, I have to get cat. Okay? If I want to get cat, I can just get cat. Okay, so for example, it is a potential deadlock and hence a bug to first obtain the fox lock and then obtain the dog lock, because the dog lock must always be acquired prior to the fox lock. So here's an example in which this would cause a deadlock. Okay, so this is a deadlock example if you do it in the wrong order. So acquire lock cat. Thread 2, acquire lock fox. Okay, so far so good. Thread 1, acquire lock dog. Now thread 2, try to acquire lock dog. Can't, go to sleep. Okay, thread 2 has fox. Thread 1 tries to acquire lock fox. Well, thread 2 is sleeping, so it didn't make any progress to release. Well, I don't have the fox lock, so I'm going to wait. Okay, now wake up, thread 2. Okay, I'm going to try to acquire the lock dog again. Well, thread 1 has it, but it's still sleeping, so nothing to do. I'm just going to wait for lock dog. Okay, thread 1 now wakes up and goes, okay, well, I'm going to try to acquire lock fox. Well, thread 2 has it. Guess I can't do anything. I'm going to wait for the lock fox and go to sleep. Well, thread 2 wakes up again. It tries to acquire the lock dog, but thread 1 already has a lock dog and it's asleep, so nothing to do. I'll go to sleep. Do you see how this is really bad? I could do this like for 10 more minutes actually, just to hammer the point. But yeah, I legitly do that actually. That's how I burned it into my head. I just did that for like 10 minutes straight when I first read this. Thread 1 is waiting for the fox lock, which thread 2 holds, while thread 2 is waiting for the dog lock, which thread 1 holds. Neither ever releases its lock and hence both wait forever. Bam! Deadlock. If the locks were always obtained in the same order, a deadlock in this manner would not be possible. That's true. So whenever locks are nested within other locks, a specific ordering must be obeyed. It is good practice to place the ordering in a comment above the lock. Something like the following is a good idea. So just like have good documentation, comment, cat lock, locks access to the cat structure. Always obtain it before the dog lock. So that means in order to get the dog lock, you need to get the cat lock. Okay. So the order of unlock does not matter with respect to a deadlock, although it is common practice to release the locks in the order inverse to in the way they were let me do it again. Although it is common practice to release the locks in an order inverse to that in which they were acquired. So basically, reverse order. Unlock in reverse order. They say it does not matter with respect to deadlock, but you should just probably release it in inverse order. So you do cat, dog, fox, then you unlock fox, unlock dog, unlock cat. So preventing deadlocks is important. The Linux kernel has some basic debugging facilities for detecting deadlock scenarios in the running kernel. These features are discussed in the next chapter. Okay. Contention and scalability. The term lock contention, or simply contention, describes a lock currently in use but that another thread is trying to acquire. Okay, the term lock contention, or simply contention, so we can just call it contention, describes a lock currently in use but that another thread is trying to acquire. Holy crap, describes a lock currently in use but that another can it just be written as the term lock contention or simply contention describes a lock that is currently in use but another thread is trying to acquire it. Okay, a lock that is highly contended often has threads waiting to acquire it. Should have just said it that way before. Oh my gosh. Okay. Yeah, definitely this is the better way to say it. So a lock that's highly contended often has threads waiting to acquire. A popular lock, basically. A lock that always wants to be acquired. High contention can occur because a lock is frequently obtained, held for a long time after it is obtained. Or both, because a lock's job is to serialize access to a resource. Meaning, a lock's job is to make sure that operations happen serially instead of concurrently. The critical region stuff. So, for this resource. So it comes as no surprise that locks can slow down a system's performance, right? Imagine you had locked like the very beginning of your program and then unlocked like at the very end of your program. And then basically you just defeated the whole point of multi-threading, because any thread that tries to just come in and do work, right? You just kind of made them go to sleep. So a highly contended lock can become a bottleneck in the system, quickly limiting its performance. So let's say you do have a critical region and that you keep using this one lock, right? That you keep spamming all over the place. Like you have like this one lock that you use to lock every critical region that you have. Well, that lock is going to be very popular because you only have that one lock that everyone uses, everyone being each thread. So then when that happens, well, a bunch of like other places where you're using that lock, for example, if any threads are there, well, basically they have to go to sleep because there's always going to be somebody using that lock. So, of course, the locks are also required to prevent the system from tearing itself to shreds. So this is what I like about reading books word for word, because the thing is that if you read books word for word, you kind of catch like these fun little imagery, I guess. And sometimes the author, you know, the book might be dry, but the author tries to make it fun. So tearing itself to shreds. So a solution to high contention must continue to provide the necessary concurrency protection. So scalability is a measurement of how well a system can be expanded. In operating systems, we talk of the scalability with a large number of processes, a large number of processors, or large amounts of memory. We can discuss scalability in relation to virtually any component of a computer which we can attach a quantity. Ideally, doubling the number of processors should result in doubling of the system's processor performance. This, of course, is never the case. Okay, so just because you 2x'd your CPU amount does not mean you 2x'd the processor performance. The scalability of Linux on large number of processors has increased dramatically in the time since multiprocessing support was introduced in the 2.0 kernel. In the early days of Linux multiprocessing support, only one task could execute in the kernel at a time. During 2.2, this limitation was removed as the locking mechanisms grew more fine-grained. Through 2.4 and onward, kernel locking became even finer-grained. Today, in the 2.6 Linux kernel, kernel locking is very fine-grained and scalability is good. The granularity of locking is a description of the size or amount of data that a lock protects. A very coarse lock protects a large amount of data. So a coarse lock is basically something that locks a big section of data, big critical region. For example, an entire subsystem set of data structure. Okay, that's a coarse. You know, it's like coarse and fine. On the other hand, a very fine-grained lock protects a small amount of data, so small critical region. Say only a single element in a larger data structure. In reality, most locks fall somewhere in between these two extremes, protecting neither an entire subsystem or an individual element, but perhaps a single structure or list of structures. Most locks start off fairly coarse, so usually, you know, they start out doing too much, trying to lock too much, but then you start to understand your data access patterns, so then you start moving that lock closer and closer to where you really truly need that lock. And that's fine. That's like experimentation. And are made of more fine-grained as lock's contentions proves to be the problem. So basically, if you find that lock, because you locked a lot and it becomes a very popular lock, maybe making it more fine-grained can help. So one example of evolving to finer-grained locking is the scheduler run queues discussed in Chapter 4, Process Scheduling. In 2.4 and prior kernels, the kernel had a single run queue. Recall that a run queue is a list of runnable processes. Early in the 2.6 series, the 001 scheduler introduced per processor run queues, each with a unique lock. The locking evolved from a single global lock to separate locks for each processor. Okay, so that's an example. You go from one big coarse lock for the queue to now separate locks per processor. This was an important optimization because the run queue lock was highly contended on large machines. Large machines being computers or servers with a lot of CPUs, CPU cores, threads, and so on. So essentially serializing the entire scheduling process down to a single processor executing in the scheduler at a time. So basically having one big coarse lock resulted basically in single threaded scheduling. So later in the 2.6 series, the CFS schedule improved the scalability further. So that's a scheduler that we went over. Generally, the scalability improvement is a good thing because it improves Linux's performance on larger and more powerful systems. Rampant scalability improvements can lead to a decrease in performance on smaller SMP and uniprocessor machines. However, because smaller machines may not need such fine-grained locking, but will nonetheless need to put up with the increased complexity and overhead, consider a linked list. An initial locking scheme would provide a single lock for the entire list. So that's like when you first implement a linked list that needs locking, you will probably do it for the entire linked list. But in time, the single lock might prove to be a scalability bottleneck on large multiprocessor machines that frequently access this linked list. Meaning that as time goes on, by having this big lock around your linked list, as you run the Linux kernel on servers with lots and lots of CPUs, this is actually going to slow things down. So in response, the single lock could be broken up into one lock per node of the linked list. So very, very fine grained. Now you're just locking per node. For each node that you want to read or write, you obtain the node's unique lock. So you can have a lot of locks, basically. Now, there's nothing stopping you from like just making more locks to make sure that you're protecting things correctly. So now there's only lock contention when multiple processes are accessing this. Now there's only lock contention when multiple processors are accessing the same exact node. What if there's still lock contention? However, do you provide a lock for each element in each node? Each bit of each element? The answer is no. Even though this fine-grained locking might ensure excellent stability on large SMP machines, how does it perform on dual processor machines? So smaller core machines. Basically, you're going to introduce a lot of overhead. Okay, the overhead of all those extra locks is wasted if a dual processor machine does not see a significant lock contention to begin with. So it's a balance. You have to kind of just measure and see, like, what it's just a cost trade-off. Like, what can you do without having to let the other one hurt too much? Sometimes you do have to let the other thing hurt a little, but you can't have everything. Nonetheless, scalability is an important consideration. Designing your locking from the beginning to scale well is important. Coarse locking of major resources can easily become a bottleneck on even small machines. There is a thin line between too coarse locking and too fine locking. Locking that is too coarse results in poor scalability if there's a high lock contention, whereas locking that is too fine results in wasteful overhead if there is little lock contention. Both scenarios equate to poor performance. So the advice is to start simple and grow in complexity only as needed. Simplicity is key. Yes, always try to stay simple. That's good advice too for life. Conclusion. Making your code SMP safe is not something that can be added as an afterthought, meaning concurrency. You can't just do concurrency at the end. You can't do synchronization for concurrency at the end. Proper synchronization, locking that is free of deadlocks, scalable and clean requires design decisions from start through finish. Whenever you write kernel code, whether it is a new system call or a rewritten driver, protecting data from concurrent access needs to be a primary concern. Provide sufficient protection for every scenario, SMP kernel preemption, and so on. And rest assured that the data will be safe on any given machine and configuration. The next chapter will discuss how we can actually do this. So this is the theory. Next chapter, we're going to go with the mechanisms, the implementations. So with the fundamentals and the theories of synchronization, concurrency, and locking behind us, now let's now dive into the actual tools that the Linux kernel provides to ensure that your code is race and deadlock free. And that's another chapter. See you all next time. Thank you.